Hello there, and welcome to the Sleepy Scientist official channel. Tonight, we're setting off on what might just be our most exciting adventure yet. A gentle, star-filled journey, told across a few cozy installments. You could think of it as a little expedition through the universe, helping us better understand where we fit in within it all, as the cosmos quietly carries on its grand story around us. Our destination for this series is the Andromeda galaxy, or, if you fancy the more formal names, Messier 31 or NGC 224. Those scientific labels do sound rather clinical, don't they? They hardly hint at its true splendor, because Andromeda isn't just a neighbor in the night sky. It's an enormous, swirling city of stars. Over 1 trillion of them, in fact, each one a glowing little furnace twinkling away in the deep. And perhaps most fascinating of all, it plays a rather important role in what lies ahead for our own little home, the Milky Way. In a way, Andromeda even shapes part of our cosmic future, a quiet but powerful influence humming along with gravity and time. But don't worry, this won't feel like a lecture. It's more like a calm, stargazing chat, stitched together with bits of ancient astronomy, a touch of modern physics, and a sprinkling of those lovely big questions about time, space, matter, and destiny. All of it softly tangled in the wonder of how wonderfully connected everything is out there. So, settle in, take a breath, and let's drift among the stars together. To the unaided human eye, in a place of deep, untouched darkness, it appears only as the faintest suggestion of something distant, a soft, almost ghostly smudge of light, a tiny blur brushed across the night sky. You'll find it tucked within the constellation of Andromeda, named for the mythical princess. For most of human history, that was all anyone ever saw of it, a quiet little mystery, fixed in the heavens, yet refusing to explain itself. The sharpest observers could note its presence, but its true nature remained far beyond imagination. Its story starts long before telescopes, with the early sky watchers of antiquity, those brave minds who first tried to make sense of the patterns above. Among them was the Persian astronomer Abd al-Rahman al-Sufi. In the 10th century, in his book of fixed stars, he described this faint glow as a little cloud, a small patch of light that clearly wasn't a star. He wrote only what he could see, unaware that he was peering across a gulf of space so immense it lies well outside ordinary human intuition. And for many centuries, that is all it remained, a gentle enigma in the night, a soft nebulous curiosity drifting just beyond understanding. With the first telescopes appearing in the early 1600s, one might have hoped the mystery of the Andromeda Nebula would finally give way to clarity. But instead, things only grew more intriguing. In 1612, the German astronomer Simon Marius looked through his modest lens and offered the first real description of what he saw. He compared its gentle glow to the flame of a candle shining through thin horn, a soft, hazy light that was unlike any familiar star. A little later, in the 18th century, the French comet hunter Charles Messier
added it to his famous list of objects that were decidedly not comets. For him, Andromeda, which he recorded as M31, was a mild irritation, a stubborn smudge in the sky that could easily be mistaken for the very discoveries he hoped to claim.
Yet his catalogue of false alarms became, quite unintentionally, one of the most treasured guides in astronomy, a map of the night's most remarkable sights. As the years unfolded, the true nature of this and other spiral nebulae remained one of the great, quietly simmering debates in science. Astronomers found themselves divided. Was Andromeda simply a nearby cloud of glowing gas? Perhaps a young solar system forming within our own Milky Way? Or was it something far more remarkable, an island universe of its own, a vast, distant realm of countless stars, so far away that their combined light softened into a pale, dreamy shimmer? It was a question that would take centuries to answer. Yet even in its uncertainty, it invited a sense of wonder, a gentle reminder of how vast and mysterious our night sky truly is.
This long-standing scientific disagreement eventually came to a rather memorable head in 1920 within the quiet halls of the Smithsonian Museum of Natural History. It wasn't a debate in the sharp, argumentative way we might imagine today, but more of a thoughtful, scholarly gathering, later known as the Scale of the Universe debate. On one side was Harlow Shapley, a bright and self-assured astronomer who had recently used the steady heartbeat of Cepheid stars in globular clusters to reveal the true astonishing size of our Milky Way. His findings gently nudged the Sun from the center of things, showing it to be just one star among many. Feeling confident in this work, Shapley maintained that the Milky Way was, in fact, the entire universe. To him, the spiral nebulae, even Andromeda, were simply small, misty structures within our own galaxy, perhaps the beginnings of new planetary systems. He leaned heavily on the claims of Adriaan van Maanen, who believed he had measured the slow turning of those nebulae. If such rotation were real, Shapley argued, the objects must be close by. After all, a far-off galaxy would appear far too still for us to notice its movement. Opposite him stood Eber Curtis, a careful and precise observer. He championed what was then called the island universe idea, the notion that these spirals were not local wisps of gas, but entire galaxies of their own, scattered well beyond the bounds of the Milky Way. He pointed out that these nebulae tended to linger far from the Milky Way's crowded plain, and that their light looked far more like starlight than the glow of gas. The discussion grew spirited at times, yet it ended without a clear resolution. Both men brought strong ideas and subtle clues, but neither held the one thing that would have settled the matter once and for all: a definite way to measure just how far those mysterious spirals truly were.
The telescope that would deliver the proof, the true hero of this cosmic tale, was the 100-inch Hooker telescope perched up at Mount Wilson. And the chap determined to use it for this great astronomical quest was a young, rather ambitious astronomer, Edwin Powell Hubble. He'd taken quite the winding path to get there, studying law, teaching at a school for a bit.
But somewhere along the way, he realized his heart wasn't really in courtrooms or classrooms. It was up there, in the stars. So each night, he pointed that magnificent telescope, truly a marvel of engineering for its time, toward the soft, misty smudge in the sky we call the Andromeda Nebula. He'd take long-exposure photographic plates, tracking the heavens ever so patiently for hours at a stretch. Not the sort of job for rushing, but one for quiet persistence and a bit of wonder. And what was he hoping to find in that gentle glow? A very special kind of star, one that could tell us how vast the universe really is. He was searching for those softly pulsating beacons known as Cepheid variables. A name that sounds a touch technical, yes, but stars that shine with a rhythm, steady and telling, like a cosmic heartbeat guiding us through the dark.
Cepheid variables are rather like the universe's own metronomes, quiet, reliable keepers of time and light. These special stars gently swell and contract, their outer layers rising and falling in a steady rhythm that plays out over days, sometimes even months. Their brightness isn't fixed. It softens and brightens again with a calm, clockwork brace. The real breakthrough in understanding them came from the remarkable work of Henrietta Swan Leavitt at the Harvard College Observatory. Studying thousands of photographic plates of the small Magellanic Cloud, she noticed something wonderfully simple and profound. The timing of a Cepheid's pulse is directly linked to how luminous it truly is. Longer pulsations mean a brighter star. This period luminosity relationship became a precious tool for cosmology. By measuring the rhythm of a Cepheid's flicker, you can know its actual brightness, its true light, and that meant, at last, you could judge just how far away it must be. Hubble's careful, patient task was to seek out these stellar lighthouses within the soft haze of Andromeda, to measure their gentle pulse. Then, by comparing their known true brightness with the faint glow we see from Earth, he could calculate their distance with a level of certainty that had never before been within reach. A quiet rhythm in the stars, opening up the scale of the universe itself. The Cepheid method sits on the second, and many would say the most crucial step, of what astronomers call the cosmic distance ladder. It's a gentle chain of techniques, each one checked and calibrated by the step beneath it, that helps us measure the vast reaches of the universe. Close to home, radar and parallax let us map the scale of the solar system and the stars nearest to us. But Cepheids, they let us reach much farther, carrying us out across the quiet darkness between galaxies. Because if you know how long a Cepheid takes to brighten and dim, you know exactly how bright it ought to be. And by comparing that true brightness with how faint it looks from Earth, you can use a simple rule of light, the inverse square law, to work out just how far away it must be. That's what Hubble did. He measured these delicate, pulsing stars in Andromeda, noted just how dim they appeared, and realized something astonishing. They were far too faint to be nearby. When he completed the calculations, checking star after star to be absolutely sure, the conclusion was quietly breathtaking. the sort of result that gently rearranges our understanding of the universe. It was, quite genuinely, a shift of cosmic perspective. The Cepheids in Andromeda were simply impossibly far away, so distant that they lay well beyond even the outermost edges of the Milky Way, as Shapley had measured it. And with that, the conclusion became quietly unavoidable. The numbers, steady and unfeeling as they were, pointed to only one answer. Andromeda wasn't part of our galaxy at all. It wasn't a nearby cloud or a curious little smudge in our cosmic neighborhood. It was its own island universe, a galaxy in its own right, vast and resplendent, perhaps even larger than the Milky Way itself. In that one gentle but astonishing moment, the size of the known universe expanded by an almost unimaginable amount. The Milky Way was no longer the lone central structure we once believed it to be. Instead, we found ourselves facing a cosmos of extraordinary breadth, a great expanse filled not just with countless stars, but with billions of other galaxies, each one a shimmering archipelago of its own. It was, in many ways, a new kind of Copernican shift, a quiet reshaping of our place in the grandness of it all, whispered to us across the depths of space.
And with that single discovery, the old idea of the great Andromeda Nebula quietly melted away, and in its place stood something far grander, the Andromeda Galaxy. It was rather like wiping the mist off a window, only to find an entire world waiting beyond it. That pale, dreamy smudge in the sky wasn't a little cloud of stars at all. It was a colossal city of light, home to over 1 trillion suns. Hard to imagine, really, but wonderfully humbling. And as we'll wander through the next parts together, you'll see it isn't some cold, distant bystander. It's part of our own cosmic story, a graceful dance partner in gravity, a great ancient neighbor with a past written in starlight, and a future that brushes gently against our own. In studying Andromeda, in a way, we're simply learning a little more about ourselves, our tiny world set within a beautifully vast galactic stage.
This single astronomical object, M31, quietly reshaped our understanding of where we belong in the cosmos. It offered a lesson that is both humbling and beautifully grand. It showed us that with patience, careful observation, and thoughtful reasoning, we can uncover truths far beyond what our senses alone could ever reveal. As you look at this image, remember that you're seeing the spark that ignited one of the greatest shifts in human thought, a revolution that didn't arrive with noise or drama, but with a faint, stubborn smudge of light and the gentle, enduring curiosity of people determined to understand it. Let that thought rest in your mind for a moment, like a soft breath in the dark. The discoveries that change everything often begin in the quietest of ways, with something small, subtle, and patiently waiting to be noticed.
Realizing that Andromeda was a galaxy in its own right was a bit like opening a door onto a landscape far larger than anyone had imagined. Hubble had handed us the key, but beyond that threshold lay an entire mansion of knowledge, room after room filled with new wonders, new puzzles, and ever deeper questions. To truly understand Andromeda, we have to wander beyond the simple fact that it exists at all. We step gently into the details, how it's built, what it's made of, and the slow, powerful forces that have shaped it over billions of years. It becomes a story of learning how to measure something enormous, how to weigh an entire galaxy, and how to see that the soft glow we observe from Earth is only a tiny hint of the vast hidden reality within. A quiet reminder that the universe is always larger, richer, and more mysterious than it first appears.
One of the first things we notice about Andromeda is simply how large it is. Saying it stretches some 220,000 light-years across can feel a bit abstract, a number far too big to settle comfortably in the mind. So it helps to imagine a little thought experiment, something to give that vastness a gentler shape. Picture a single photon of light, the quickest traveler in the entire universe, setting off from one edge of Andromeda and heading all the way to the other. Even while racing along at about 300,000 kilometers per second, that tiny particle would still need around 220,000 years to finish the journey. In that length of time, here on Earth, humanity would have gradually transformed from early Homo sapiens into the complex, technologically capable species we are today. All of recorded human history, from the first cities along the rivers of Mesopotamia to the digital world we now live in, would pass in what amounts to little more than a soft blink, compared to the time it takes light to cross this single galactic island. And that is Andromeda's first quiet lesson for us. The scales of the cosmos work on a level so different from our own that they gently remind us how small a slice of time and space we truly inhabit.
Beautiful as that glowing disk is, it turns out it isn't the true edge of the galaxy at all. For quite a long time, astronomers thought that where the light tapered off, the galaxy's influence did too. A fair assumption, really, but one that turned out to be quite wrong. Because the real size of a galaxy isn't drawn in starlight. It's drawn in gravity, gentle, invisible, and ever-reaching. The clue that finally set things right came from studying how galaxies spin, something first cracked open in the 1970s, thanks to brilliant work by astronomers like Vera Rubin and her collaborator Kent Ford. What they did was rather clever and rather patient too. They measured how fast stars and gas clouds move at different distances from a galaxy's center, including our lovely neighbor Andromeda. Using the laws first set out by Johannes Kepler, things should slow down the farther out you go, just like in our own solar system, where Pluto drifts in its orbit far more slowly than speedy little Mercury nearer the Sun.
Only that isn't what they found. Not at all. Instead, the stars and gas way out in the outskirts of Andromeda kept orbiting quickly, almost the same speed as the ones closer in. Imagine if every planet circled the Sun at an identical pace, no matter the distance. Utterly odd and utterly fascinating. The only explanation was that there had to be far more mass there than anything we could actually see. Not more stars exactly, but more something, spread out in a vast, rounded halo surrounding the bright disk, holding the outer stars in its steady gravitational embrace. That unseen mass, tugging on everything quietly from the dark, is what we now call dark matter. And this was the first solid proof of it, hiding in plain sight, not as light, but as motion.
The dark matter halo is, in many ways, the true body of the Andromeda galaxy. That graceful spiral we admire in photographs is really just the glittering adornment it wears on the outside. Beautiful, of course, but only a small part of the whole. According to our best models, shaped by studies of how Andromeda bends light and how its little companion galaxies move around it, this dark halo may span more than 2 million light-years. It's so large that it's already brushing up against the dark matter halo of our own Milky Way, even though the bright parts of the Jew galaxies still sit about 2.5 million light-years apart. Long before the visible stars meet, their invisible envelopes are quietly touching in the realm of gravity. And the mass of this halo is almost unimaginable. Andromeda's trillion stars and all the gas and dust between them make up only a few 100 billion solar masses. But when you include the dark matter, the total rises to well over 1 trillion, perhaps even around 1.5 trillion solar masses. More than 90% of Andromeda's mass is unseen, revealed only by the gentle but unyielding pull it exerts on the tiny portion that glows.
When we begin to understand this quieter, hidden framework beneath a galaxy, it becomes easier to appreciate the graceful movement we see on the surface. Those familiar spiral arms, lovely as they appear, aren't solid or fixed in place. If they were, the steady rotation of the galaxy would twist them tighter and tighter until the pattern disappeared entirely within a few 100 million years. Yet galaxies as old as Andromeda still show these elegant spirals, clear as anything. So astronomers needed a new way of thinking, which arrived in the form of something called density wave theory. Put forward by C.C. Lin and Frank Hsu, the idea is really quite gentle. The spiral arms aren't built from the same stars all the time. Instead, they're more like slow-moving traffic on a cosmic motorway. A wave of slightly higher density sweeps through the galactic disk, much like a soft ripple passing through still water or a sound wave traveling through air.
When clouds of gas and dust drift into this wave, they're gently pressed together. That tiny nudge is often enough for them to collapse under their own gravity, giving rise to new stars, big, bright, and wonderfully short-lived. These young blue stars light up the spiral arms, tracing out their shape. But the stars themselves don't stay put. They wander in and out over time. Even our own sun, as it journeys around the Milky Way, slips through the galaxy's spiral arms roughly every 100 million years or so. The arm, in truth, is a wave of star formation, not a rigid structure. In Andromeda, we can see all of this with remarkable clarity. Its spiral arms are adorned with a soft pinkish glow, immense H2 regions where hydrogen gas has been gently ionized by the intense ultraviolet light of newborn stars. The largest of these glowing regions are true stellar nurseries, vast and active, each one a grander and more energetic cousin of the Orion Nebula in our own night sky.
When we look up at Andromeda's star-forming regions, we find they aren't sprinkled about evenly, and that little detail, rather lovely though it sounds, opens yet another part of its long story. If we switch to ultraviolet light, which lets us spot those hot, bright, baby-young stars, something quite striking appears. A glowing, near-circular ring of starbirth, sitting about 30,000 light-years out from the center. Astronomers sometimes call it Andromeda's Ring of Fire, but don't let the name fire you up too much. Think of it as a soft halo of renewal, shining with quiet intensity. Why is it there? Well, one leading idea, backed by gentle, whirring computer simulations, is that billions of years ago, Andromeda had quite the dramatic encounter, a head-on collision with a sizable companion galaxy. Not the sort of bump you'd brush off, mind you, but a deep, ancient ruffle in the fabric of its disk. A bit like dropping a pebble into a calm pond, sending ripples outward, except on a galactic scale, unfolding over eons.
Those ripples, a wave of density traveling through the stars, may well be what sparked that ring of concentrated star formation we see today. A fingerprint of a lively, storm-touched past. And while it might sound like a quiet theory told before bedtime, we actually have proof that these cosmic collisions happen more often than you think. The Gaia has mapped the precise motions of stars in our own galaxy, revealing very similar ancient run-ins. A lovely bit of reassurance that galaxies growing through collisions isn't just possible, it's rather ordinary, part of their nature, woven into their slow evolution. So, though Andromeda looks calm and serene in the sky, it carries the gentle scars of a very spirited youth, reminding us that even the quietest giants have stories worth telling. At the center of this wide, graceful disk with its swirling, star-forming arms lies the galactic bulge, a great, rounded gathering of stars that forms the galaxy's quiet central hub. Unlike the disk, where stars move in neat, orderly paths, the bulge is a place of more wandering, unpredictable motion. Most of the stars here are ancient, around 10 billion years old or more. Their light carries a soft golden hue, the warm glow of aging suns that have long since used up the hydrogen in their cores and now burn heavier elements instead.
These stars are also what astronomers call metal-rich, meaning they hold more of the heavier elements compared with the stars in the galaxy's outer halo. Those elements were created in the hearts of the earliest massive stars and scattered across space when those stars ended their lives in brilliant supernovae, enriching the gas that later formed the bulge. This central region is the galaxy's old, settled heart, a place where the once frenzied pace of starbirth has eased into a deep and lasting calm, leaving behind a dense, steady population of long-lived ancient stars.
That central bulge we chatted about earlier, lovely and luminous though it is, isn't quite the same all the way through. With sharper eyes, especially from the wonderfully nimble Hubble Space Telescope and some rather clever ground-based observatories using adaptive optics, astronomers spotted something tucked right inside it, a nuclear star cluster. It's a fairly small patch by galactic standards, only a few dozen light-years across, but absolutely crammed with stars. In fact, the crowding there is millions of times denser than what we're used to in our own corner of the sky. Rather dazzling to picture, isn't it? Imagine standing on a quiet little planet in the midst of that cluster. Night wouldn't really feel like night at all. Your sky would shimmer with thousands of stars as bright as Venus, always glowing, always near, so the darkness never quite settles in. A starry twilight that never truly fades.
Now, why such a bright little crowd sits at Andromeda's heart is quite a story in itself. It's thought to be the leftover core of a smaller galaxy that drifted a bit too close long ago, tugged in by gravity, gently unraveled at the edges, and drawn right to the center of its new home. Over time, its dense core sank inward through a process called dynamical friction, a bit like a pebble slowly settling into sand, until it found itself snug at the very heart of Andromeda. Not quite a violent ending, perhaps, but certainly a thorough one. Another hint of how galaxies grow, shift, and quietly borrow from one another over billions of years. A gentle reminder that even the calmest skies are shaped by quite marvelous histories.
At the center of this wide, graceful disk, with its swirling star-forming arms, lies the galactic bulge, a great, rounded gathering of stars that forms the galaxy's quiet central hub. Unlike the disk, where stars move in neat, orderly paths, the bulge is a place of more wandering, unpredictable motion. Most of the stars here are ancient, around 10 billion years old or more. Their light carries a soft golden hue, the warm glow of aging suns that have long since used up the hydrogen in their cores and now burn heavier elements instead. These stars are also what astronomers call metal-rich, meaning they hold more of the heavier elements compared with the stars in the galaxy's outer halo. Those elements were created in the hearts of the earliest massive stars and scattered across space when those stars ended their lives in brilliant supernovae, enriching the gas that later formed the bulge. This central region is the galaxy's old, settled heart, a place where the once frenzied pace of starbirth has eased into a deep and lasting calm, leaving behind a dense, steady population of long-lived ancient stars. So, this at last is the true makeup of a galaxy like Andromeda. Not just light that we can admire, but gravity we can feel, even when it's invisible. A beautiful blend of the seen and the unseen, working together in quiet harmony. There's the vast dark matter halo holding everything in its gentle grip. The softly warped gaseous disk whispering of old encounters. Those graceful spiral arms, not fixed lines but rolling waves of creation.
and the ancient starry bulge at the core, steady and wise after billions of years of cosmic living. Then, sprinkled around the edges, is the star-dusted local group like a surrounding family, each smaller galaxy leaving little traces of itself behind along the way.
What we've learned, really, is that a galaxy isn't a still photograph. It's more like a long-lived, quietly changing world, an ecosystem shaped over unimaginable time, growing, shifting, interacting, forever carried along by gravity's invisible hand. We've gone from seeing Andromeda as a faint blur in the sky to understanding it is a proper star-filled metropolis. And in doing so, we've begun to pick up the universe's own soft, whispered language, the gentle rhythm of stars in motion, telling us where everything has been and perhaps where it's slowly headed next. A comforting thought, in a way, that the cosmos has a story and we're simply one little part of it, listening in, learning bit by bit, and floating gently along with the rest.
Our journey so far has given us a gentler, deeper way of seeing, a sense of the hidden structure beneath Andromeda's lovely spiral glow. But to truly understand a galaxy, we have to wander into its more secretive corners, its energetic heart, its turbulent past, and the faint, ancient traces that still drift around it. From here, our exploration drifts into the frontier of modern astrophysics, where the laws of physics are stretched almost to breaking, and the story of cosmic evolution is written in the quiet remains of events long past. We'll ease our way toward the gravitational storm at Andromeda's center, sift through the scattered clues left by stars it has absorbed over time, and listen, as best we can, for the subtle hints of dark matter shaping it all. This isn't just a gentle tour of features, it's more like a careful, soothing investigation into the life of a galaxy, uncovering its history, one soft whisper at a time.
One of the most intriguing places in Andromeda, and really in any large galaxy, is its very center. It's here that the number of stars rises to a brilliant peak, gathered into a compact, glowing core. For many years, astronomers wondered what this luminous heart truly was. Perhaps it was simply the natural thickening of the galactic bulge, a region where countless stars were packed so closely together that their light blended into one soft radiance. Or perhaps something a little more unusual was hiding there, something far more powerful. Clues began to appear through spectroscopy, the gentle art of teasing starlight apart into its different colors. Using larger and ever more sensitive telescopes, astronomers turned their attention to this tiny central region.
By measuring tiny shifts in the light, the slight reddening or bluing caused by stars moving towards or away from us, they could trace how fast those stars were traveling. And what they discovered was truly remarkable. The stars nearest the center were racing around at extraordinary speeds, thousands of kilometers per second, circling an unseen point with incredible urgency.
To keep stars moving that fast in such snug, tight orbits requires an immense gravitational pull. And the only thing capable of producing such a concentrated mass is a supermassive black hole.
The evidence for a whopper of a black hole right at Andromeda's center, what astronomers call M31 star, is really quite extraordinary. It comes from years of patient observation, watching individual stars loop around something massive and unseen, almost like tracing the path of moths circling a hidden lantern. By tracking those starry orbits so carefully, scientists can dust off the trusty laws of Johannes Kepler and use them to weigh whatever sits in the middle. And those stars oblige, moving in neat little ellipses, their speeds and distances quietly giving the game away. When the suns are done, and they've been checked more times than a scientist cares to admit, they point to something astonishing, around 100 to 150 million times the mass of our Sun, squeezed into a space smaller than our own solar system. There simply isn't a cluster of objects we know of that could sit so tightly packed without tipping over into becoming a black hole. It's the only answer that truly fits.
And if you like a mental picture to take with you into drowsiness, the edge of this black hole's reach, its event horizon, the point of no return, would span roughly the width of Mercury orbit. Not that it's anything to fret about, mind. It's all happening wonderfully far away in the quiet of deep space. This wasn't just to find about one galaxy either. It gently nudged open a bigger truth about the universe. These supermassive black holes aren't outliers or oddities. They're part of the usual furniture in most hefty galaxies, including those in our own cosmic neighborhood, the local group. A rather lovely, soothing thought, really, that galaxies and their black holes seem to grow up together in a slow, gravitational partnership written in starlight and motion.
The story of Andromeda's center is even more intricate and intriguing than it first appears. For quite some time, detailed images from the Hubble Space Telescope revealed something rather surprising. The very heart of the galaxy didn't look singular at all. Instead of one bright central point, there seemed to be two distinct patches of light. This curious feature sparked a long-running question. Could Andromeda actually host two supermassive black holes? It's an idea that fits quite neatly with what we know about how galaxies grow. If Andromeda built itself up by gently absorbing smaller galaxies, and many of those smaller galaxies had black holes of their own, then those black holes would slowly drift inward, eventually settling into the center. They might even form a pair, circling one another for billions of years before finally merging.
According to the leading explanation, though, the double nucleus isn't the black holes themselves, but two tight clusters of stars. One cluster orbits the main black hole at the true center. The second, slightly offset cluster appears to be the preserved core of a smaller galaxy that Andromeda swallowed long ago, a dense little knot of stars that may still cradle its own black hole,
gently orbiting the primary one in a slow cosmic waltz. The physics here is wonderfully complex, with these star populations tugging and weaving around one another. And while the brighter of the two clusters now seems to mark the actual central black hole, the possibility of a second, quieter black hole hidden within the offset cluster remains very much alive, a soft, lingering mystery tucked into the heart of the galactic machine.
The neighborhood around Andromeda's big central black hole isn't a quiet one in terms of physics. There's a lot going on there that would make a scientist's heart flutter, though from a vast, safe distance, it all feels rather serene. At the moment, M31 star isn't gobbling up huge amounts of matter. It's what we'd call quiescent, or having a bit of a cosmic snooze. Not fully asleep, mind you, more like dozing lightly. The clever folks using the Chandra X-ray Observatory have noticed a small but steady flicker of X-ray light coming from exactly the same spot. It's thought to be caused by a very thin, very warm little whirl of gas and dust drifting around in what's known as an accretion disk. A gentle glow in the dark, really, nothing frantic, more like the ember of a hearth after the fire's settled down. Even while it's dozing, stray bits of gas from passing clouds or little puffs from nearby stars, their stellar winds, if you like, occasionally wander too close and feel that tug of gravity. And once they do, they begin to spiral inward, forming that warm, swirling disk. The friction inside it heats everything up enormously, millions of degrees sort of hot, which makes it shine softly but brilliantly in X-rays. Now and then, a slightly chunkier clump might drift in too, perhaps the tatty leftovers of a star that got a touch too close, sparking a brief little flare before settling back down. Again, nothing for us to lose sleep over, but fascinating to observe. And this quiet little X-ray whisper matters more than you might think. By studying a black hole in this calm state, astronomers can understand both its gentle, sleepy moments and the rare occasions when it fully wakes. It's a comforting reminder, really, that even the giants of the universe breathe softly, stretch occasionally, and carry on, guided by gravity's invisible hand in the long, quiet night.
The central black hole and all its quiet power is deeply tied to the wider story of the galaxy. A story that isn't written in the bright, crowded core, but out in the soft, faint regions far beyond it. Andromeda's stellar halo, which we've already pictured as a gentle, diffuse sphere, is in truth something like a cosmic archive, part graveyard and part archaeological site. It's out here, in these dim outer reaches, that the clearest evidence of Andromeda's appetite is found. The idea of galactic cannibalism might sound dramatic, but it's really just a natural part of how galaxies grow.
In the early universe, tiny clumps of stars drifted together, merging again and again to form the larger structures we see today. And that process hasn't stopped.
big galaxies like Andromeda and our own Milky Way continue to expand by slowly absorbing the small dwarf galaxies that wander too close. Andromeda, being the heavier of the two great galaxies in our local group, has been especially effective at this gradual gathering in. Over billions of years, it has folded countless smaller systems into its halo, each leaving behind a faint, lingering trace, a gentle reminder of the long, quiet history that shapes the galaxy we see today. The proof for Andromeda's quiet cosmic appetites isn't just a theory anymore. It's written across the sky in the form of stellar streams. These are delicate, river-like trails of stars, gently curving and looping around the galaxy, each one a remnant of a smaller galaxy that ventured too close and was gradually drawn apart by Andromeda's steady, unyielding gravity. A remarkable effort called the Pan-Andromeda Archaeological Survey, PANDAS, using the Canada-France-Hawaii telescope, has been key in tracing and cataloging these streams. They show up as faint, coherent chains of stars, not random, but patterned, almost like delicate threads weaving through space.
One of the most striking is the giant stellar stream, a grand loop containing billions of stars, once part of a fairly substantial dwarf galaxy that Andromeda slowly absorbed over the last few billion years. By carefully measuring the speed and chemical makeup of these stars, astronomers can piece together the story of that little galaxy, its mass, its composition, even the precise way it was dismantled. It's a level of cosmic forensics that would have seemed like pure imagination a generation ago. And yet, here it is, the quiet, lingering traces of Andromeda's past, flowing like gentle rivers of light, whispering tales of encounters long ago, if only you know how to look.
But the halo holds more than delicate streams of starlight. It also shelters a small family of surviving companion galaxies, a quiet snapshot of Andromeda's gravitational reach. Among the most well-known are Messier 32, or M32, and Messier 110, M110. M32 in particular is something of a mystery. It's a compact elliptical galaxy, appearing almost like a bright, tightly packed knot of stars pressed right up against Andromeda's disk. Its behavior is unusual. It has no young stars, no gas, and its remaining stars move at surprisingly high speeds within a very small space.
The best explanation is rather dramatic beneath its calm appearance. Astronomers believe M32 was once a much larger spiral galaxy that wandered too close to Andromeda's center. During that close approach, Andromeda's tidal forces acted almost like a cosmic scalpel, stripping away M32's outer layers, its stars, its gas, even much of its dark matter. What's left is the sturdy, tightly bound core, the part strong enough to survive the encounter. M32 is, in a sense, a galactic survivor, a faint echo of what it once was, slowly spiraling inward and destined eventually to be fully absorbed.
Its presence so near the main galaxy serves as a gentle reminder of the quiet but powerful interactions that have shaped Andromeda's recent past.
In contrast, M110 is a rather more typical dwarf elliptical galaxy, a soft, diffuse little puffball of older stars. It's currently going through a gentle process of tidal disruption. In very deep images, astronomers can make out faint streams of stars being quietly tugged away from it, hinting at the galaxy's eventual fate. Though there's no rush, it's a slow, graceful unfolding over cosmic time. Looking at M32 and M110 together is like reading two chapters of the same story. M32 shows us the dramatic later stages of a close encounter, a galaxy that has been deeply reshaped by its interactions.
M1110, on the other hand, is more subdued, giving us a glimpse of an earlier, gentler phase of disruption. Side by side, they reveal the long, unfolding tale of galactic evolution. And beyond these two brighter companions, Andromeda is surrounded by dozens of much fainter dwarf spheroidal galaxies, tiny, shadowy systems, each containing only a few million stars and dominated by dark matter. These little galaxies are the building blocks of larger structures, pristine remnants from the early universe still holding on to their secrets. They are, in a way, quiet laboratories where we can study the subtle workings of dark matter on a small scale, guided almost entirely by its invisible hand. A calm, patient reminder that even the smallest and faintest corners of the cosmos have stories to tell if we only take the time to look.
The process of accretion doesn't just influence the smaller, captured galaxy, it also plays a part in shaping the larger one that absorbs it. When a gas-rich dwarf galaxy is drawn in, it brings with it a fresh reserve of cold, untouched hydrogen. This gentle stream of gas can sink into the host galaxy and provide new material for forming stars. It's quite likely that some of the bright star-forming rings and bursts we see scattered across Andromeda's disk were set in motion by events just like this. In this way, an accretion not only adds mass, but also gives the galaxy a kind of quiet rejuvenation, sparking fresh waves of stellar birth. And during the merging process, some of that gas can be nudged inward, drifting ever closer to the central black hole.
Andromeda isn't shining as a quasar today, but it's entirely possible that in earlier, more dramatic periods of its history, its central black hole, M31 star, was actively feeding, glowing with the radiance of 1 billion suns as it consumed great quantities of infalling gas. The growth of the galaxy and the growth of its central black hole are, in many ways, simply two parts of the same slow cosmic story.
And so we arrive at one of the most intriguing, almost whispering mysteries of Andromeda, its dark matter. We've already seen that it makes up the vast majority of the galaxy's mass, stretching out in an enormous, unseen halo. Yet, despite its immense presence, it remains elusive. What exactly is it?
We know it's there because of gravity, quietly shaping the motions of stars and galaxies alike. But it doesn't shine. It doesn't absorb light. It doesn't reflect it either. And it seems to barely, if at all, interact with the ordinary matter we're familiar with. It's almost like a hidden hand guiding the galaxy without ever making a sound.
One of the ways scientists hope to catch a glimpse of it is indirect. They look for the gentle traces left behind if dark matter were to annihilate or decay. Some leading ideas, especially those involving weakly interacting massive particles, or WIMPs, suggest a delicate possibility. When two dark matter particles meet, they could cancel each other out, transforming their mass into energy. That process might release a quiet cascade of particles, including gamma rays, the most energetic form of light, faint signals drifting across the vast emptiness, whispering secrets of this hidden cosmic substance. It's a subtle, almost poetic reminder that the universe holds much more than meets the eye, and that even the unseen can shape the grand, flowing rhythm of galaxies like Andromeda.
And this is where Andromeda becomes something rather special, a kind of natural laboratory on a truly cosmic scale. In 2017, astronomers working with data from NASA's Fermi Gamma Ray Space Telescope uncovered an intriguing surprise: a faint, diffuse glow of gamma rays coming from Andromeda's center. In our own Milky Way, gamma rays tend to gather along the galactic plane, produced as cosmic rays collide with clouds of gas. But in Andromeda, the glow seemed different, more rounded, more evenly spread out, matching the shape we'd expect from its dark matter halo.
It was a quietly thrilling discovery. There are other possible explanations, of course, such as a hidden population of millisecond pulsars, tiny, rapidly spinning neutron stars, too faint to pick out individually. But even so, the idea that this glow might hint at dark matter interactions remains a compelling and rather tantalizing possibility. If it were ever confirmed, it would be the first indirect yet clear sign of dark matter at work in a galaxy beyond our own, offering valuable clues about what this mysterious substance might truly be. In this sense, Andromeda isn't just a galaxy we look at with curiosity. It's a frontier for particle physics as well, a vast, quiet detector for one of the universe's most elusive ingredients.
When we put all the pieces together, the supermassive black hole at its heart, the curious binary nucleus, the flowing stellar streams, the little satellite galaxies, and that faint halo of gamma rays, a picture begins to emerge. It's a complex, layered biography of the Andromeda galaxy. It all began over 10 billion years ago as a small clump of dark matter in the very young universe. Slowly, gently, it drew in gas, giving birth to its first stars. Over the eons, a series of mergers, some dramatic, some subtle, shaped it into the majestic spiral we see today. Each encounter left a mark, warping its disk, building its bulge, scattering stars into its halo, and perhaps feeding the growth of that immense central black hole.
And yet, When we gaze at Andromeda now, it looks calm, almost serene. Its quiet beauty hides a lively, dynamic history, a tale of collisions and reconstructions, of gravity sculpting its form over billions of years. To understand Andromeda is to understand that a galaxy is never truly still. It is a living, evolving entity. Its past is written in the faint fossils of its halo, and its future rests quietly in the dark, unseen embrace of its invisible mass. A gentle reminder, really, that even the grandest structures in the cosmos carry their history softly within them if we take the time to look.
We've now gathered the full picture of our celestial neighbor. We've traced both its visible and hidden structure, wandered into the restless brightness at its heart, and read the clues of its past in the faint stars that surround it. And all of this knowledge leads us quietly and inevitably to one remarkable conclusion. The peaceful motion we see today is only the beginning. The Milky Way and Andromeda are not simply two galaxies passing one another in the dark. They're bound together by gravity, partners in a slow and graceful dance that over billions of years will draw them closer and closer. In time, that gentle pull will lead to a dramatic union, reshaping them into an entirely new kind of galaxy. What comes next is a projection, a glimpse into the far future, guided by the steady, unchanging laws of physics. It's a tale of both destruction and creation, played out on the grandest of stages. And its earliest lines are already being written, quietly in the precise measurements our telescopes are making today.
In a deep, breathy, soft British BBC narrator voice, perfect for sleep and relaxation, no dramatic tone. The certainty of this future collision doesn't rest on a simple glance at the sky, but on a careful, many-layered effort from observational astronomy. The first hint came from something quite striking: Andromeda's blue shift. In a universe where almost every galaxy is drifting away from us, and their light is stretched to redder wavelengths, Andromeda stands out as a quiet rebel. Its light is shifted toward the blue, which tells us it's moving in our direction. This was noticed as early as 1912 by Vesto Slipher at Lowell Observatory, a curious finding at the time, one that only truly made sense once Hubble later showed just how far away Andromeda actually was. But knowing it's coming towards us isn't quite enough. To understand what kind of encounter awaits, we also need to know its sideways motion, the gentle drift it makes across the sky, called its tangential motion. If that sideways motion is very small, the collision will be more or less head-on. If it's large, the galaxies might only skim past each other in a kind of cosmic near miss. For decades, though, measuring this motion was almost impossibly delicate, a task a bit like trying to judge the speed of a tiny snail making its way across the surface of the moon. Yet astronomers persisted, patiently gathering the clues needed to see how our neighbor is truly moving through the dark.
The breakthrough came courtesy of the European Space Agency's Gaia mission, a truly remarkable endeavor designed to chart the positions, distances, and motions of over 1 billion stars in our own Milky Way with astonishing precision. But Gaia's keen eye reaches even further, allowing astronomers to track the motions of individual stars in nearby galaxies, including our grand neighbor Andromeda. By carefully comparing the ultra-precise positions of these stars over time, scientists have been able to measure Andromeda's proper motion, that is, its very slight drift across the sky against the more distant, stationary quasars. The results, published in a series of landmark studies, leave little room for doubt.
Andromeda isn't merely passing by on a gentle curve. It is headed almost directly towards us. Its sideways motion is remarkably small, less than 20 kilometers per second, a tiny fraction of its approach speed of 110 kilometers per second. When these motions are fed into sophisticated computer simulations, taking into account the pull of gravity from both galaxies and the subtle counterforce of dark energy, the picture becomes clear. Someday, far in the future, a direct merging collision between Andromeda and the Milky Way is inevitable. A quiet inevitability written in the language of stars and gravity, unfolding on a timescale so vast that it feels almost dreamlike.
The timeline of this future meeting is as astonishing as its inevitability. Our universe is about 13.8 billion years old, and the entire story of the Milky Way and Andromeda coming together will span almost 10 billion years, from their first gentle approach to their final blending into one. It's a stretch of time that nearly matches the age of the cosmos itself. To bring it a little closer to home, imagine compressing the whole history of Earth into a single calendar year. On that scale, the merger would unfold slowly and steadily over more than 8 months. It isn't a single event at all, really. It's an era, a long and quiet chapter written across the vastness of time. The first act of this grand cosmic dance will begin in roughly 3.75 billion years. By then, Andromeda will have grown into a truly spectacular sight in our night sky, a sprawling, softly glowing disk stretching perhaps the width of 20 full moons. Over the following few 100 million years, it will gradually swell, its spiral arms becoming ever more distinct, gently unfolding before our eyes. Around 4.5 billion years from now, the two galaxies will make their first close approach. This won't be a violent crash, like two cars colliding in space. Rather, it will be a slow, graceful gravitational dance, a complex, almost hypnotic tango choreographed by the invisible hand of gravity. The first signs of the encounter will appear in their spiral arms, the outer stars and gas, feeling a gentler pull than those nearer the center, will be flung outward, forming long, luminous tidal tails, enormous streams of stars, gas, and dust that arch gracefully across hundreds of thousands of light-years of intergalactic space. These flowing rivers of starlight are not unusual. We can see them in other interacting galaxies today, like the famous antennae galaxies, where the dance has progressed a little further. From within our own Milky Way, the familiar band of the night sky would be completely transformed. It would give way to a chaotic, brilliant vista, rivers of stars stretching into the void, and the looming, distorted core of Andromeda commanding the heavens in all its grandeur.
When the two galaxies make their first pass, they will interpenetrate, weaving through one another in a slow, majestic dance. It's important to understand that this is a collision of gravity, not of stars. The spaces between individual stars are so vast that the chance of any two actually crashing into one another is practically zero. To imagine this, picture each star as a single grain of sand. The average distance between stars in a galaxy would then be several miles. Now, if you were to throw 2 handfuls of such sand into a space the size of a continent, almost none of the grains would ever touch. In other words, galaxies are mostly empty space.
But the gas and dust that floats between the stars, the interstellar medium, behaves quite differently. Unlike the stars, this material is continuous, and when the Milky Way and Andromeda pass through one another, their clouds of gas and dust will collide. Massive molecular clouds from our galaxy will meet those from Andromeda at hundreds of kilometers per second. It's not a gentle interaction, it's a supersonic shock, a dramatic meeting of cosmic material, yet one that unfolds slowly and gracefully across millions of years.
The physical effects of this meeting of gas clouds are quite remarkable. As they collide and compress, they'll spark a dramatic surge in star formation, a phenomenon astronomers call a starburst. During this period, stars will begin forming at rates far beyond what we see today, perhaps 10 times faster, 100 times faster, or even more. The merging galaxies will glow with the bright blue-white light of millions of new, massive stars coming to life in quick succession.
These stellar nurseries will be far more energetic than anything we see now in either the Milky Way or Andromeda, giving rise to enormous clusters of hot, brilliant O-type stars, dazzling giants that shine intensely and live only briefly. In many ways, it's like a final rush of creation, a grand luminous flourish before the newly formed galaxy settles into a long, gentle quiet. And alongside this burst of new stars, there will also be countless supernovae, the most massive stars, burning through their fuel in just a few million years, will end their lives in spectacular explosions, scattering freshly made heavy elements into the surrounding gas, enriching the galaxy for whatever comes next.
So, what might all of this mean for our own little corner of the cosmos, our solar system? Astronomers have explored this carefully using intricate N-body simulations, modeling the gravitational tugs and pulls of hundreds of billions of particles. And the results are, in their own way, both reassuring and a little disorienting. The good news is that the chance of the Sun being completely ejected from the merged galaxy is very, very small, less than 1%. The combined gravitational field of the two galaxies is simply too cohesive for that to happen. But the more likely scenario is that our solar system will be nudged into a quite different orbit. We might find ourselves drifting outward into the galactic halo, far from the bright, bustling core, where the night sky is dominated by the fading glow of the newly merged galaxy.
Or perhaps we could be gently slingshotted inward toward the crowded central regions where stars cluster far more densely and the light of new star formation would be dazzling and overwhelming. Either way, the constellations we have known for thousands of years, those familiar patterns traced by nearby stars, would be scattered, lost among the alien stars of Andromeda. The night sky, which has felt so constant and steady throughout human history, would become an entirely new, shifting and dynamic canvas. A gentle reminder, really, that even the heavens we take for granted are ever-changing, part of a slow, majestic dance that unfolds on timescales far beyond our own. After that first disruptive encounter, the two galaxies, now held together by gravity, like partners linked by an invisible thread, won't merge straight away. Instead, they'll drift outwards to a point of maximum separation, an apocenter, perhaps hundreds of thousands of light years apart. And then, much like two yo-yos tugged gently back along a string, they'll begin their slow return toward one another. Their orbits gradually decay through a process called dynamical friction. As each galaxy moves through their shared dark matter halos, it stirs the surrounding material ever so slightly, leaving a faint gravitational wake behind it. This wake pulls back on the galaxy, gently stealing a little of its energy and momentum. Over 1 billion years or more, they will pass by each other again and again, each encounter softening their once defined spiral shapes, drawing out long streams of tidal debris and guiding more and more gas toward their centers. It is a slow, graceful dance, patient, inevitable, and deeply woven into the fabric of cosmic time. The final merging of the two galaxies, the moment when they truly become one, won't happen for another 6 or 7 billion years. By then, the graceful spiral shapes we recognize today will have vanished. The galaxies will have become irregular, somewhat chaotic collections of stars, their neat, orderly rotations replaced by more random, gentle motions. As they finally coalesce, the system will go through what astronomers call violent relaxation. Despite the dramatic name, it's a slow, natural process. The ever-changing gravitational pull of the merging galaxies gradually redistributes the energies of all the stars. Over time, they settle into a new, stable arrangement, shaped by the combined mass of the merged system. and the end result is likely to be a smooth, largely featureless, and gently rounded object, an elliptical galaxy. The spirals, the arms, the once familiar forms will have dissolved, leaving behind a quiet, steady structure that hints at the long, intricate dance that brought it into being. It's a calm, inevitable transformation on a scale so vast it almost feels like the universe itself is breathing.
This future galaxy already has a name, Milkomeda. It will be a vast elliptical system, carrying within it the combined weight of its ancestors, several trillion stars gathered into one immense whole. Its light will take on a soft golden hue, shaped mostly by old, gently glowing red stars. By then, the age of lively star formation will have faded. The gas that once fueled new stars will have been used up in earlier bursts of creation, swept away by the collective force of countless supernovae, or heated so intensely that it can no longer cool and collapse into fresh starlight. Milkomeda will be a galaxy in its later years, grand, steady, and serene, though without the youthful spirals and graceful arms it once inherited. And in this quieter era, it will stand as the dominant gravitational presence in the local group, its vast pull guiding the motions of the remaining dwarf galaxies for ages still to come.
The final act of this grand cosmic story will unfold in the very heart of Milkomeda. The supermassive black holes from both galaxies, having gradually made their way to the center through the gentle tug of dynamical friction, will finally meet. They will form a binary pair, circling each other within a tiny region of space, just a few light years across. For billions of years, they will dance this delicate, slow waltz, their orbit gradually shrinking as they lose energy by nudging away stars that wander too close. The ending arrives in a dazzling and utterly extraordinary way. As the two black holes draw ever nearer, their energy begins to escape, not through interactions with stars, but in the form of gravitational waves, ripples in space-time itself, as Einstein predicted.
They spiral inward, faster and faster, and in the final moments before merging, they unleash an astonishing burst of gravitational energy, equivalent to billions of supernovae all exploding at once. It will be one of the most energetic events in the universe since the Big Bang, a fleeting distortion of space-time that in the far future could be detected by instruments like the Laser Interferometer Space Antenna, LISA, across the cosmos. The black holes will merge into a single colossal entity, weighing in at over 150 million times the mass of the Sun. And even then, in the quiet aftermath, it may recoil from the uneven emission of gravitational waves, nudged gently yet perceptibly several thousand light-years away from Milkomeda's exact center.
This grand story, from the first approach of the galaxies to the eventual merging of their central black holes, is more than just a forecast for the Milky Way and Andromeda. It is, in a sense, a universal tale.
Observations from the Hubble Space Telescope have shown us that galaxy interactions and mergers were far more common in the early, denser universe. The enormous elliptical galaxies we see today at the hearts of rich clusters are the Milkomedas of the past, the final results of countless such cosmic dances. By studying the impending encounter between our own Milky Way and Andromeda, we are fortunate to witness a fundamental process unfolding right in our cosmic neighborhood. We can see how galaxies grow, transform, and recycle their stars and gas on the grandest of scales. The dance of these two great spirals is a local example of a universal principle. The cosmos is never still. It is in constant, dynamic change, often gentle, sometimes violent, but always orchestrated by the quiet, persistent hand of gravity. And in this slow-motion ballet, the music plays over billions of years. We, here and now, have a privileged view of the first steps of this epic performance, a performance that will shape the future of our corner of the universe long after our sun has faded and our world is a distant memory, yet whose echoes we can glimpse tonight in the soft light of the stars above. We've glimpsed both the future and the distant past of the Andromeda galaxy, yet our journey isn't complete without pausing to appreciate its role in the present, as perhaps the single most important astronomical object beyond our own Milky Way. Andromeda is far more than a distant subject of study. It is a cornerstone of modern cosmology, a celestial laboratory where we calibrate our instruments, test our deepest theories, and quietly extend the limits of human understanding. Its closeness allows us to see it not just as a faint point of light, but as a vast, resolvable playground for discovery, a kind of cosmic Rosetta Stone. Through it, we can begin to interpret the faint echoes of the early universe, translating them into a language of physics that makes sense to us here on Earth. This chapter, then, is devoted to appreciating how Andromeda has shaped and continues to shape our understanding of the cosmos, from the intimate lives of stars to the grand architecture of space-time itself. One of Andromeda's most profound contributions to astronomy lies in its role in helping us understand stars, and more broadly, the cosmic distance ladder. Before Hubble's groundbreaking work, our knowledge of stars was largely limited to the Milky Way. We couldn't be sure whether stars in other galaxies followed the same physical laws, experienced similar life cycles, or existed in comparable varieties. Andromeda changed all of that. By resolving countless individual stars within its sprawling arms, it offered a rich and statistically significant sample of stellar populations entirely separate from our own galaxy, free from the veil of dust that obscures so much of the Milky Way. For the first time, astronomers could conduct a true comparative census of stars. They could study how different types of stars are distributed, their brightness, their colors, and discovered beautifully that the same rules applied. The Hertzsprung-Russell diagram, which relates a star's brightness to its temperature, worked perfectly in Andromeda, just as it does at home. Nuclear fusion,
stellar evolution, the dramatic mechanics of supernovae, all these processes were revealed to be universal, operating identically across millions of light years. In other words, Andromeda taught us that the cosmos, vast as it is, follows a gentle, consistent order. The same quiet principles guiding stars here, out there, and everywhere in between.
What makes Andromeda truly remarkable is our ability to resolve its individual stars. And this is precisely what allows it to serve as a cornerstone for the cosmic distance ladder. You might picture this ladder as a series of carefully connected steps, each one relying on the one below it, helping us measure the vast scale of the universe. The first step is geometric, using parallax to gauge the distances to nearby stars. This was the work of the European Space Agency's Hipparcos and Gaia missions, quietly building the foundation. But parallax only carries us so far, a few thousand light-years at most. That's where Andromeda comes in, with its bright Cepheid variable stars providing the next vital rung.
By carefully calibrating the relationship between a Cepheid's pulsation period and its intrinsic brightness, using the distances measured within our own Milky Way, astronomers could then apply this cosmic ruler to the Cepheids in Andromeda, giving the first direct primary measurement of distance to another galaxy. This single step anchors the entire ladder. Every subsequent rung, whether it's RR Lyrae stars, the tip of the red giant branch, or the brilliant peak luminosities of Type 1a supernovae, ultimately depends on that foundational measurement. So when we say a galaxy in the Virgo cluster lies 50 million light-years away, or that a distant quasar is billions of light-years across the void, the accuracy of that statement traces all the way back to the Cepheids in Andromeda. It is, quietly and elegantly, the bedrock of our map of the observable universe.
Beyond its role as a cosmic measuring stick, Andromeda is also a wonderfully accessible laboratory for understanding how galaxies are built and structured. From our vantage point within the Milky Way, our view is necessarily limited and often obscured, much like trying to understand a vast forest while standing among a handful of trees. Andromeda, in contrast, presents itself nearly face-on, offering a clear, unobstructed view of its sweeping spiral arms. This perspective allows astronomers to study its architecture in exquisite detail, including the spiral density waves that organize its stars and gas into graceful patterns. By carefully measuring how different parts of the galaxy rotate, not just tracking the stars, but also observing clouds of neutral hydrogen that emit their subtle 21-centimeter signal, scientists have been able to construct the most detailed map yet of a galaxy's gravitational field beyond our own. And this map quietly tells a remarkable story. The rotation curve of Andromeda remains flat far beyond the visible edge of its disk, showing us that the stars we see are only a part of the picture. They are embedded in a far larger, unseen halo of dark matter, a vast and invisible mass that gently holds the galaxy together. It's a beautiful illustration of the hidden architecture of the cosmos, revealed to us through careful observation and a little patience. The study of Andromeda's interstellar medium is a world of its own. Because it is so close, telescopes across the spectrum can explore its composition and motions in exquisite detail. Radio observatories, like the Very Large Array, have traced the cold neutral hydrogen, revealing a vast warped outer gas disk stretching far beyond the familiar stellar disk, a subtle fossil of past gravitational encounters. Sub-millimeter instruments, such as ALMA, peer into the cold, dense molecular clouds where stars are born, even identifying complex organic molecules, the very ingredients that, in principle, could seed life in a galaxy beyond our own. Infrared eyes, like those of the Spitzer and James Webb telescopes, see through the obscuring dust, mapping older stars and uncovering hidden stellar nurseries tucked away in the galactic disk.
Meanwhile, the Chandra X-ray Observatory unveils the high-energy universe, the hot, diffuse gas filling Andromeda's halo, X-ray binaries where black holes and neutron stars feed on their companions, and the lingering remnants of stellar explosions. Taken together, this multi-wavelength view transforms Andromeda from a simple two-dimensional silhouette into a rich three-dimensional ecosystem. It allows us to follow the full life cycle of matter, from cold, dark clouds to brilliant newborn stars, to the hot, diffuse plasma that drifts throughout the galaxy, revealing a cosmos in constant motion, quietly and beautifully alive.
Andromeda's value as a cosmic laboratory extends even into the exotic and extreme. It's a prime place for catching rare and fleeting astronomical events, simply because we can watch millions of its stars individually, night after night. Over the years, Andromeda has hosted several observed supernovae, the most famous being SN 1885A, the very first supernova ever recorded in another galaxy. Today, modern surveys continue to keep a watchful eye, searching for microlensing events, where the gravity of an unseen object, a star, a planet, or perhaps even a black hole, briefly magnifies the light of a more distant star.
These subtle flickers allow astronomers to map out the population of invisible compact objects in Andromeda's halo, offering tantalizing clues about the nature of dark matter. Even the search for gravitational wave sources is informed by Andromeda. By studying potential progenitor systems like pairs of neutron stars, scientists gain a deeper understanding of the dramatic cosmic events detected by LIGO and Virgo, placing them in a wider galactic context. In this way, Andromeda serves as a gentle but powerful teacher, letting us observe both the quiet rhythms of stars and the sudden dramatic flourishes of the universe, all from a safe, contemplative distance.
Perhaps one of the most fascinating and ongoing quests in modern astronomy is the search to understand dark matter, and Andromeda sits at the very forefront of this investigation. As we've seen, its rotation curve first provided the classic hint of something unseen, quietly shaping the motions of stars. But astronomers have gone much further than that. By carefully tracking the movements of Andromeda's satellite dwarf galaxies and the globular clusters scattered throughout its halo,
They can map the gravitational pull of its dark matter in 3 dimensions. These objects act like little test particles, moving through the invisible field, their orbits tracing the shape of the halo itself, whether it is nearly spherical, gently flattened, or more irregular. Current observations suggest that Andromeda's halo is relatively spherical, a detail that carries clues about the properties of the dark matter particle, since some theories predict flatter or more elongated halos. And then there's the mysterious gamma-ray glow detected by the Fermi telescope, radiating softly from Andromeda's center in a pattern that could hint at dark matter interactions. It's an exciting, though still unconfirmed, clue. Should future, more sensitive instruments be able to confirm this and pinpoint its source, Andromeda may well become the place where dark matter is seen not just as a gravitational mystery, but as a tangible particle, bridging the quiet vastness of the cosmos with the world of fundamental physics.
In a deep, breathy, soft British BBC narrator voice, perfect for sleep and relaxation, no dramatic tone. The philosophical lessons we take from studying Andromeda are as vast and sweeping as the galaxy itself. In many ways, it has been the quiet agent of a series of cosmic humblings for humanity. The Copernican principle reminded us that Earth is not the center of the solar system. Shapley showed that the Sun is not the center of the Milky Way. But it was Hubble's work on Andromeda that delivered perhaps the most profound realization of all. Our galaxy is not the universe. We are one small part of a cosmos containing at least 2 trillion galaxies in the observable universe.
It's a staggering thought, one that humbles the imagination and gently reminds us of our smallness in scale. And yet, at the same time, it is deeply affirming. From this tiny world, guided by mathematics and the laws of physics, we have measured the distance to another island of stars, inferred the presence of invisible matter shaping its mass, and even predicted its distant collision with our own galaxy. In that sense, we are small, yes, but our minds are capable of seeing and understanding the universe in ways nothing else in nature can. Andromeda reminds us both of our humility and our extraordinary capacity for wonder. Andromeda also acts as a kind of mirror, reflecting the past and future of our own Milky Way. By studying its gently warped disk, we glimpse the ancient collisions that may have shaped our galaxy long ago. Mapping its stellar streams reveals a more evolved version of structures like the Gaia sausage, the remnants of past accretion events we are only beginning to uncover in our own halo. Observing its quiet, central black hole gives us a sense of perspective on the behavior of our own Sagittarius A star, while forecasting the eventual merger with the Milky Way allows us to read a glimpse of our galaxy's ultimate destiny. In this way, Andromeda transforms from a distant, faint smudge of light into something far more intimate, a close relative, a cosmic twin, sharing a fate that will one day entwine with our own. And finally,
Andromeda stirs the imagination with the possibility of life beyond our own little world. With 1 trillion stars, the number of potential planets is almost unimaginable. Though we cannot see them directly, studies from missions like Kepler suggest that millions of Earth-sized worlds could be orbiting in the gentle, life-friendly zones around their stars. The same quiet processes that gave rise to life on Earth, the gathering of water, the slow assembly of complex molecules, the steady energy of a sun, are likely at work there as well. In that sense, Andromeda is a vast reservoir of potential biospheres, each one a whisper of possibility.
Any civilizations that might exist there would see our Milky Way as a faint, delicate spiral. When they look at us, they are seeing light that began its journey before humans had even appeared. Our two galaxies are connected not only by gravity, but by a timeless exchange of light, a soft, cosmic dialogue across space and time. In contemplating Andromeda, we are not merely studying another galaxy, we are placing ourselves in the wider story of the universe, asking whether the silence we feel is empty or full of quiet life waiting to be discovered. And perhaps in some far-off future, when our galaxies finally merge, it might not just be a meeting of stars and dust, but a gentle, unimaginable convergence of worlds, of minds, reaching toward one another across the vast cosmic archipelago.
Our journey through the Andromeda galaxy has carried us from the initial, almost humbling revelation of its existence to the delicate, intricate mechanics of its eventual collision with our own Milky Way. But to truly grasp the meaning of this cosmic event, we must look beyond the simple story of two spirals merging. We need to explore the subtle astrophysical processes that will shape this transformation, to imagine the new universe of observations that might one day greet any future inhabitants of Milkomeda, and to gently confront the ultimate thermodynamic destiny that awaits all stellar systems. This chapter invites us to consider the galactic ecosystem in its fullest sense, the slow cycling of matter, the quiet flow of energy, and the long-term evolution that will unfold over trillions of years in the post-merger era. It's a story of patience and scale, of transformation that is both inevitable and profoundly beautiful, whispered across the vast expanse of time.
The merging of the Milky Way and Andromeda isn't just a single event, but a long, intricate process that will reshape the way ordinary matter behaves within the system. This ordinary matter, the atoms that build stars, planets, and even us, makes up less than 5% of the galaxy's total mass. Yet it's responsible for all the light and structure we see. At the moment, both galaxies are moving through a fairly steady rhythm, something like a galactic metabolism. In their spiral arms, cold gas gently collapses to form new stars. Those stars then fuse hydrogen and helium into heavier elements as they burn. When the most massive of them reach the end of their lives, they explode as supernovae, enriching the surrounding space with fresh metals and sending powerful waves of energy through the interstellar medium. These explosions heat nearby gas, creating vast bubbles and fountains that can lift material out into the galactic halo. Over time, some of that gas cools and drifts back down into the disk, ready to begin the cycle again. It's this ongoing rhythm, this constant renewal, that gives spiral galaxies their bright bluish arms and their steady, ongoing birth of new stars.
The merger will gently yet profoundly unsettle the delicate balance of these galaxies. As their interstellar clouds collide, a dramatic burst of star formation will ignite, a brief but intense period when stars are born at a staggering pace. For a few 100 million years, the galaxies will pour forth new stars as if in a furious, almost frenzied creation, consuming as much gas in that short span as they might normally use over many billions of quiet years.
It is a time of brilliant, almost overwhelming energy, but one that cannot last. The very stars that illuminate this era are also its agents of change. Their powerful winds and eventual supernovae stir and heat the surrounding gas, making it too turbulent to collapse into new stars. Thousands of these stellar explosions, happening in close succession, can even sweep gas out of the disk entirely, flinging it into the halo or beyond, reshaping the galaxy's structure. This cosmic feedback is a remarkable form of self-regulation, a gentle reminder that even in the universe's most spectacular moments of creation, there is a balance, a quiet rhythm that guides the life and death of galaxies across the ages. The transformation into an elliptical galaxy, the Milkomeda of the distant future, is a gentle, inevitable consequence of gas exhaustion and heating. Without a fresh supply of cooled, dense gas, the galaxy can no longer maintain its elegant, rotating spiral disk, nor can it give birth to new stars. In this quiet but profound transition, the beautiful, ordered spiral arms will dissolve forever. What remains is a more spheroidal arrangement of stars, their orbits scattered and randomized by the gentle turbulence of the merger, a subtle reshaping of the galaxy's very structure. Over time, the color of the galaxy itself will shift. The bright blue-white glow of young, hot stars will fade, giving way to the warmer, redder light of an aging stellar population. Astronomers often call this change the difference between blue and star-forming galaxies and red and dead ones. Milkomeda will join the latter. Its stars will continue their quiet life cycles, the most massive ones burning out first, leaving behind the long-lived lower-mass stars. Slowly, imperceptibly, over countless eons, the galaxy will fade and redden, a serene testament to the passage of cosmic time. The role of the central supermassive black holes in this grand dance cannot be overstated. During the merger, as gas is drawn inward by tidal forces and dynamical friction, it provides a final, spectacular feast for these cosmic giants. It is quite possible that at the peak of their encounter, both M31 star and our own Sagittarius A star will enter periods of intense activity, shining as luminous active galactic nuclei. Their brilliance could outshine the combined light of all the stars in the galaxy.
This energetic output doesn't just dazzle, it stirs and heats the surrounding gas, gently dispersing the remaining star-forming material and helping to bring new stellar creation to a quiet pause. And finally, the black holes themselves will merge, sending ripples of gravitational waves across the fabric of space-time, the last dramatic signature of unity in the birth of the new galaxy. It is a quiet, majestic conclusion to a story written in light, gravity, and motion across billions of years. For any planetary systems that endure this billion-year upheaval, the changing sky would be a spectacle both awe-inspiring and unsettling. The slow, graceful approach of Andromeda would give way to a period of celestial chaos. During that first close passage, the constellations we know so well would vanish entirely, replaced by the brilliant, unstructured glow of hundreds of billions of unfamiliar stars from the approaching galaxy. Tidal tails would stretch across the heavens as immense glowing arcs, painting the sky with patterns never seen before.
The frequency of nearby supernova would rise, occasionally bathing planets in bursts of energetic radiation. And as the stellar density increases in the inner regions of the merging system, the likelihood of close stellar encounters would grow, with wandering stars passing near planetary systems, gently or sometimes dramatically nudging their orbits and sending comets from distant clouds tumbling inward. The familiar, steady astronomical clocks that civilizations might have relied on for navigation and timekeeping would be gone, replaced by a dynamic, unpredictable sky. A constantly shifting, dazzlingly complex tapestry that would inspire both wonder and a quiet sense of unease. Yet after this turbulent period, a new and enduring stability would emerge. Once Milkomeda has fully formed and settled, the night sky from within it would be unlike anything we know today. For a planet orbiting a star in the outer halo, the sky would appear relatively dark, yet suffused with a faint, omnipresent glow from the combined light of countless stars, stretching in an ellipsoidal haze. The familiar, majestic band of the Milky Way would no longer be there. Closer to the core, however, the night would take on a very different character. The density of stars would be so great that the sky would never truly darken. Instead, a deep, perpetual twilight would prevail, with thousands of stars shining as brightly as Venus to the naked eye. In such a world, the very concept of night might lose its meaning. This would have fascinating consequences for any astronomers on such a planet. Without the familiar dark band of a spiral galaxy to guide them, mapping the structure of their galaxy might be more challenging. Yet they would enjoy an unparalleled vantage point for studying stellar populations and the complex motions of stars. From the brilliant, crowded sky, they might even infer the presence of the central supermassive black hole far earlier than we did, simply by observing the rapid, intricate dance of stars in their luminous heavens.
Looking far beyond the merger, to the ultimate fate of Milkomeda, invites us to ponder the long-term destiny of all galaxies in an expanding universe.
We are living in what astronomers call the stelliferous era, the age of stars, but even this luminous chapter is not eternal. Over the coming 100 trillion years, the stellar population of Milkomeda will slowly dim. The smallest, longest-lived red dwarfs will be the last to shine, their faint light stretching across the quiet galaxy. Even these humble stars will eventually exhaust their fuel, cooling gently into black dwarfs, cold, inert spheres of carbon and oxygen, emitting no light at all.
In time, the galaxy will become a dark, silent collection of black dwarfs, neutron stars, black holes, and planets, all quietly orbiting the central supermassive black hole. Occasionally, a rare collision or a sudden accretion event might send a brief flicker of light across this shadowed realm, but these will be fleeting moments in a cosmos that has grown ever darker and more serene. It is a contemplative vision, a reminder that even on the grandest scales, the universe moves through cycles of light and quiet, birth and eventual rest.
The expansion of the universe adds yet another, even deeper layer to this distant future. Observations tell us that the expansion is accelerating, driven by the enigmatic force we call dark energy. In tens of billions of years, all galaxies beyond our local group will have drifted so far away that their light can no longer reach us, stretched and redshifted beyond detectability, forever beyond our grasp. Milkomeda, along with its remaining satellite galaxies, will become a solitary island in an ever-widening cosmic ocean, a galaxy island with no external sources of light or matter.
In the far, far future, even the supermassive black holes will slowly fade, evaporating through Hawking radiation over unimaginably long timescales, exceeding a Google of years. It is a distant, theoretical horizon, yet it hints at a universe in which even the grandest structures eventually dissolve into a faint, diffuse haze of fundamental particles. A quiet, almost serene end to the cosmic story.
The story of Andromeda and the Milky Way is in many ways just one chapter in the vast unfolding biography of the universe. It is a chapter of structure and interaction, of brilliant but fleeting flashes of stellar light. By studying this impending collision in such detail, we are doing more than predicting the future of two galaxies. We are glimpsing the life cycle of cosmic structures themselves. We are witnessing the very processes that over billions of years have built the enormous elliptical galaxies we now see in galaxy clusters. We see how star formation is regulated, how galactic shapes are transformed, and we are gently reminded of the impermanence of all things, even on the grandest scales. This merger is at once a creation story, a story of destruction, and a story of transformation. Two elegant spirals will eventually become a single, vast, serene elliptical galaxy, a testament to the quiet, enduring power of gravity
and a humbling reminder that even the age of stars will one day fade.
Our journey through the science, history, and destiny of the Andromeda Galaxy has been a sweeping voyage across space and time. We have explored its structure, traced its collision course, and pondered the ultimate fate of Milkomeda. Yet, there is one final dimension to this journey, one that moves beyond astrophysics and into the realm of human curiosity, the limits of understanding, and the nature of consciousness in a universe that can seem at once vast and indifferent. This is not merely a conclusion. It is a gentle projection forward, a quiet contemplation of the future of cosmic inquiry that Andromeda allows, and a reflection on the profound questions this faint smudge of light has inspired. Questions about our place, our knowledge, and our capacity to marvel at the cosmos.
Andromeda's role as a cosmic laboratory is far from complete. In many ways, it is only just beginning. The next generation of telescopes promises to reveal layers of the galaxy that remain hidden to us today. The James Webb Space Telescope, with its remarkable sensitivity to infrared light, is already transforming our view of Andromeda's stars. By peering through the dusty lanes that obscure so much visible light, JWST can take a full census of star formation throughout the spiral arms and central bulge. It can even detect the faint, low-mass red dwarfs that make up the majority of Andromeda's stellar population, stars that hold the key to understanding the galaxy's total mass and its chemical evolution in exquisite detail.
Beyond that, JWST's spectroscopic capabilities allow astronomers to examine the atmospheres of individual stars, creating a richly detailed chemical map. This chemical tagging lets us trace the origins of different stellar groups, distinguishing those born within Andromeda itself from those captured from devoured satellite galaxies. In this way, the telescope is helping us write a far more complete and intimate biography of the galaxy's history, layer by layer, star by star. But the future stretches far beyond the capabilities of the James Webb Space Telescope. Planned 30-meter-class ground-based observatories, such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will pair enormous light-gathering power with sophisticated adaptive optics. Their clarity will be so fine that they'll be able to resolve individual stars not only across Andromeda's crowded disk, but deep within its central bulge and nuclear star cluster. In essence, these instruments will allow us to track the subtle motions of stars in the very heart of Andromeda with a precision approaching what Gaia has achieved for our own galaxy. This will make it possible to construct a dynamic three-dimensional movie of stars swirling around the supermassive black hole M31 star, offering the most stringent tests yet of general relativity in such a strong gravitational field, and perhaps even directly imaging the black hole's sphere of influence.
By following these intricate orbits, astronomers may finally resolve the long-standing mystery of whether Andromeda's central black hole is a solitary leviathan or a close binary, a slow gravitational dance at the heart of a neighboring galaxy, unfolding over millions of years, yet visible to us from our small vantage point across the void.
The search for planets in Andromeda is a truly monumental challenge, one that may take a century or more to accomplish. The primary methods we use to find exoplanets, watching for transits or measuring the gentle wobble of a star, simply don't work at such vast distances. Yet the future offers tantalizing possibilities. Microlensing surveys, for instance, monitor the brightness of millions of stars in Andromeda, and occasionally a planet orbiting a foreground star can cause a brief, subtle brightening. Such events are rare, but even a handful could provide the first glimpse of a planetary system beyond our own galaxy, a discovery of truly epochal significance.
Looking further ahead, advanced space-based interferometers with multiple telescopes flying in precise formation across thousands of kilometers could one day achieve the resolution needed to directly image giant planets around the brightest stars in Andromeda. The confirmation of a planet there would break the final barrier of planetary science, showing that planet formation is not unique to our Milky Way, but a universal process playing out across the vast intergalactic void. In that moment, the trillion stars of Andromeda would transform from distant abstract points of light into potential solar systems, each with its own family of worlds, quietly expanding the canvas upon which the possibilities for life might be painted.
This inevitably brings us to perhaps the most profound question Andromeda inspires: the question of life and intelligence beyond our own world. The Drake equation, that probabilistic framework for estimating the number of communicative civilizations in our galaxy, becomes almost dizzying when we apply it to a galaxy with 1 trillion stars. Even if only a tiny fraction of stars host life-bearing planets, the sheer number of worlds in Andromeda makes it hard to imagine it is entirely barren. And yet, it confronts us with the Fermi paradox all the more starkly. Where is everybody? If life and intelligence are common, Andromeda should be brimming with it. Its massive, ancient stellar populations, particularly in the bulge, hint that any civilizations there could be billions of years ahead of us. Conceivably, their activities might harness energies on a truly grand scale, detectable across the intergalactic gulf.
Astronomers have even included Andromeda in searches for technosignatures, unusual signals, perhaps the glow of Dyson spheres, peculiar laser emissions, or artificially modulated starlight that could betray the presence of advanced technology. Yet the galaxy presents itself to us in serene silence. Its quietness, in fact, is a profound observation. Life, or at least intelligent, technologically expansive life, may be exceedingly rare, fleeting, or deliberately hidden. And so Andromeda sits there, a billion-star sphinx, silently posing a riddle about the nature of life in the cosmos, a riddle we are only just beginning to learn how to ask.
The approaching merger adds a remarkable, almost poetic dimension to our contemplation of existence. This collision is more than a physical process. It is a story unfolding across time and space, with a beginning, a middle, and an end, set on a stage of almost unimaginable scale. For any conscious beings that might arise within either galaxy, this narrative would form the backdrop to their entire existence. A civilization emerging in the Milky Way 1 billion years from now would watch Andromeda slowly approaching, its arrival marking the central defining event of their cosmic epoch.
Their history, their culture, their science, all might be shaped by the knowledge of this inevitable confluence. Similarly, a civilization in Andromeda would see our galaxy as a destined companion, quietly moving toward a shared future. Would such knowledge inspire them to reach for the stars, to attempt interstellar, perhaps even intergalactic journeys to safeguard their species? Might it spark profound works of art, philosophy, and science, all devoted to observing and understanding the transformation of their home? In this sense, the merger offers a shared cosmic destiny for two separate islands of life, a quiet, unifying narrative that, in principle, could provide a common purpose for intelligence emerging in either galaxy.
Finally, our study of Andromeda also reflects something deeply human. The way our minds and philosophies have grown over time. The story of our understanding of this galaxy is, in many ways, a miniature portrait of the scientific journey itself. It began with myth and simple naked-eye observation, that faint little cloud in the night sky. Then came the instruments that extended our senses, as the telescope revealed its hazy, nebulous form.
Our comprehension was forged through debate and spirited intellectual challenge, the famous Great Debate, and ultimately reshaped by a discovery that was both elegant and definitive: Hubble's measurement of Cepheid variables. Here was empirical evidence, coupled with careful mathematics, revealing the true scale of the cosmos. Andromeda is a perfect example of the scientific method at work. It shows us our unique human capacity to extend our perception through technology, to reason beyond the limits of our immediate surroundings, and to uncover profound truths about the universe, patiently, step by step. It is a reminder of how far curiosity, diligence, and careful observation can carry us, even across billions of light years. In the deep, faint glow of Andromeda, we can see the very essence of human curiosity. It speaks to our boldness, the courage to measure the seemingly immeasurable, to anticipate what lies unimaginably far away, and to place ourselves within the sweeping narrative of cosmic evolution. Andromeda is, in a sense, a bridge stretching across 2.5 million light-years of space, a bridge back to the dawn of modern cosmology, and a bridge forward to discoveries that will be made by generations of scientists we may never meet. It is both a subject of study and a symbol of the human spirit's quiet determination to explore, to understand and to seek meaning in the vast, dark, and endlessly beautiful universe we are so fortunate to call home. As our journey draws to a close, we carry with us more than facts about a distant galaxy. We carry a deeper sense of our own ability to comprehend the cosmos and a gentle, humbling wonder at the grand, interconnected story of which we are a small, conscious part. We have reached the final stage of this grand expedition. From the first faint, naked-eye glimpse of a celestial ghost, we have traveled to the intricate, multi-wavelength mapping of a metropolis of 1 trillion suns.
We have descended into the swirling heart of its supermassive black hole, traced the fossilized remnants of galaxies it has devoured, and projected its future across billions of years. A slow, graceful ballet of destruction and creation, shaping a new galactic entity. We have placed Andromeda at the heart of modern cosmology, as both a cornerstone and a living laboratory for exploring the deepest laws of the universe. Now, as we gently draw this exploration to a close, it is time to weave these threads into a single contemplative picture. Andromeda is more than an astronomical object. It is a central character in the story of our universe and in the story of humanity awakening to the cosmos. This final reflection is both a celebration and a quiet eulogy, a meditation on the fleeting, spiraling beauty of galaxies, and a soft, hopeful gaze toward the distant future where intelligence continues to ponder and participate in the evolving dance of the universe. The story of Andromeda, at its very heart, is a story of connection. It links us to the distant past. Every photon that reaches our telescopes is a tiny messenger from an age long before humans walked the Earth, carrying within it the quiet record of stars being born and dying, of galaxies colliding, and of gentle, gradual evolution. When we study its light, it is a kind of cosmic archaeology, revealing the fossil record of galactic assembly. The ancient metal-poor stars in Andromeda's halo connect us to the earliest epochs of the universe, to that first glimmer of light when galaxies began to emerge from the scaffolding of dark matter.
The warps in its gaseous disk, the looping stellar streams, all point back to dramatic events from billions of years ago, allowing us to reconstruct the timeline of its growth and transformation. Andromeda is, in a very real sense, a living archive. To study it is to learn to read this vast billion-year chronicle, a story that ties together the past, the present, and, in some small way, our own place within the grand sweep of cosmic history.
At the same time, Andromeda gently reaches forward, connecting us to the distant future. Its steady, inevitable approach, measured with incredible precision by our most advanced instruments, offers humanity a remarkable and rare gift: foresight. We are likely the only generation in the Milky Way's long history to glimpse its ultimate destiny. We exist in a fleeting, privileged moment after we have developed the tools to make such predictions, yet billions of years before the event itself will unfold.
That knowledge transforms our view of the cosmos.
We are not merely passive observers of a quiet night sky. We are aware participants in a grand, unfolding narrative. The universe is not static, and we are not detached. We are witnesses to a single dramatic act in an ongoing cosmic play. This foresight also binds us in a quiet, almost intimate way to the countless generations that will come long after us, whether they be biological beings or perhaps some future intelligence of another form, inheriting the Milky Way and eventually the merged galaxy known as Milkomeda. In this sense, we are the ancestors who first looked at the stars and began to understand the destiny they quietly foretold.
This sense of connection across time is matched by a connection across space. Andromeda stands as a kind of cosmic benchmark, a Rosetta Stone that has allowed us to take the knowledge we've gathered close to home and translate it into a universal language. The laws of thermodynamics, gravity, and nuclear physics, painstakingly worked out within our own solar system and galaxy, have been tested over and over across the vastness of intergalactic space by observing Andromeda.
The reliable rhythms of Cepheid variables, the predictable stages of stellar life, the ever-present dark matter halos, all of these affirm something deeply reassuring. The universe is coherent and ultimately comprehensible. From our laboratories here on Earth to the heart of a galaxy 2.5 million light-years away, the same rules apply. It is a profoundly humbling thought. The cosmos is not a random, chaotic expanse, but a beautifully intricate, knowable system. Andromeda offered us the key to unlock this understanding, showing that human curiosity, paired with careful observation and clever technology, can reveal the workings of reality on the grandest of scales.
And yet, for all the profound connections and cosmic insights, the story of Andromeda is also one of transience and gentle loss. The magnificent spiral we admire so much is, in the grand scheme of the universe, a temporary thing. Its elegant form relies on a delicate balance of rotation, gravity, and the ongoing cycle of star formation. A balance that can be quietly but irrevocably undone by a single major encounter. The approaching collision with the Milky Way is not a rare catastrophe. It is part of the natural rhythm of galactic life. In the universe's youth, galaxies met and merged frequently in a far more turbulent age.
The serene, grand spirals we see today are simply the survivors of that earlier chaos, holding their beauty for a time. Andromeda and the Milky Way, in their eventual union, will follow this familiar path, merging, reshaping, and transforming, their spiral forms giving way to a larger, redder, more tranquil elliptical galaxy. In studying Andromeda, we are quietly observing a fleeting era, a last glimpse of these grand, stately spirals before their eventual metamorphosis. There is a soft, almost wistful melancholy in this understanding, a gentle nostalgia for a beauty that in time will pass, a reminder of the impermanent yet exquisite nature of the cosmos.
This brings us to Andromeda's final and perhaps most profound lesson.
what it tells us about intelligence and civilization in a cosmos ruled by such vast, impersonal forces. The sheer scale of this galaxy, with its trillion stars and millions of potential worlds, gently challenges any notion of human uniqueness. The Copernican principle reminds us that we are not special. The universe and galaxies like Andromeda ought to be brimming with life. Yet the silence is profound. This great silence, set against the brilliant backdrop of Andromeda, is one of the most striking mysteries in all of science.
It asks us to ponder whether advanced, observable intelligence is extraordinarily rare, or whether it is perhaps fleeting, a stage that civilizations pass through before fading or transforming in ways we cannot yet perceive. Andromeda, in its serene vastness, becomes a mirror for our own hopes and fears, a canvas where we imagine the possibility of cosmic companionship and confront the weight of cosmic solitude. It is a quiet reminder that the universe is far larger and stranger than we can fully grasp. Yet it also invites us to wonder, to question, and to keep searching.
And yet, within this challenge lies a quietly profound responsibility and a gentle new sense of purpose. If, against all odds, we are the first, the only, or among the very few conscious minds to have emerged in our local cosmos, then our role takes on a remarkable significance. We become, in a sense, the universe's way of becoming aware of itself. The light of Andromeda, traveling across millions of years without a conscious eye to witness it, now falls upon a species capable not just of seeing it, but of understanding its origin, its history, and even its destiny.
In that moment, we are like the nervous system of the cosmos, awakening to its own grandeur, tracing the lines of its story through our curiosity and our care. The pursuit of science, then, is never merely a cold or detached act. It is, at its heart, a gentle and meaningful exploration of self, of the universe discovering itself through us. Our desire to understand Andromeda is more than a quest for knowledge. It is the cosmos quietly, tenderly reflecting upon its own nature.
Looking ahead, the legacy of Andromeda will continue to unfold in ways both profound and inspiring. It will be the first extragalactic destination for future planet-hunting missions, a key benchmark for refining the cosmic distance ladder, and the nearest example of a grand galactic merger for generations of astrophysicists to study. It will spark wonder in poets, artists, and philosophers alike, for as long as humanity gazes upwards. And in around 4 billion years, when its vast disk begins to fill our night sky, it will become the most commanding and breathtaking presence above us, a gentle, constant reminder of the immense cosmic forces that quietly shape our existence.
In the end, the story of the Andromeda Galaxy is, in many ways, our own story.
It is the tale of a species on a small, unremarkable planet orbiting an ordinary star in a quiet corner of a spiral galaxy, yet using the power of thought and imagination to reach across the vastness of space and understand the nature of a colossal neighbor. It is a quiet testament to curiosity, to patience, and to the astonishingly beautiful and sometimes humbling universe we are part of. The light of Andromeda serves as a gentle bridge of understanding, a flowing river of knowledge, a soft beacon guiding us toward a deeper sense of our place among the stars. We began this journey with a faint, elusive smudge in the night sky. We end it with a cosmos slowly unfolding before us, a destiny patiently embraced and a luminous legacy that will continue to inspire wonder and reflection for countless generations to come.